Hello, everybody in Lecce. My name is Melanie Schranz, and I will talk about unlocking the nature's secrets for the future edge cloud continuum using swarm intelligence. So, what we want to achieve in ACES is an autopoietic system. The term originates from biology, where it describes living organisms that continuously regenerate and maintain the structure despite external disturbances. So, a distributed edge cloud computing system behaving like this is highly responsive, dynamic, and resilient. By emphasizing the power of swarm behavior inspired by the natural efficiency of ants, the agility of fish, and the coordination of bees, we are creating a highly reactive and adaptive system that transforms workload allocation into a dynamic process where tasks are distributed and managed with remarkable efficiency and resilience, optimizing resource utilization and performance across edge computing environments. Imagine now being part of such a fascinating swarm, a community where every member counts. This is the magic of swarm intelligence, the key to autopoiesis. In this swarm, we are all equal yet unique. Following simple local rules, we communicate with our neighbors. It sounds quite simple, right? But from this, something extraordinary emerges. Without central control, we develop amazing abilities as a swarm. We adapt quickly, show incredible robustness, and scale effortlessly. Emergence is a secret, so a higher order arising from our local interactions. These natural principles inspire us to think differently. In a complex world, the swarm shows us that true strength comes from simplicity and collaboration. And a world where collaboration isn't just a buzzword, but a powerful force of nature, welcome to ACES, where agents work together with the wisdom of a swarm. In this system, we don't rely on a single mastermind. Instead, we work with the collective intelligence of the many. So each agent contributes to a greater whole. Like ants seeking the best food for their colony, our agents tirelessly search for optimal solutions. They make decisions locally, yet their impact is felt globally. So through ACES, we are not just allocating workloads, we are orchestrating a symphony of efficiency. We're adapting to change in real time, optimizing processing and minimizing latency. So this brings us to the agents in ACES. What we have there. So we consider an edge continuum that is built up with interconnected cluster heads, each managing a pool of resources of, for example, CPUs, storage, or GPU that present our resource agents. On the other hand, we have the incoming microservices. As we work already quite close to Kubernetes, we chose pods that have specific resources and efficiency and present our demand agents. So, this agent based modeling brings some challenges to consider. This includes the consideration of the hardware as a pool of resources, then different application types that needs to be processed by the continuum, including long running applications, batch or stream processing, and relationships among the pods, like interpod relationships, parallel processing, and dependencies. For further details, I'd like to refer the audience to one of our papers that you can see here in the slides. So for this paper, we also got awarded the Best Paper Award in the beginning of this year. So let's explore the heart of ACES. It is the emergent scheduler. So in this system, pods and resources aren't just passive entities, they are active agents. They act, interact, and make decisions autonomously. So this dynamic interplay leads to something remarkable. Scheduling emerges from the bottom up in real time. So there is no central controller dictating every single move. Instead, the system self organizes. The result is a scheduler that's inherently adaptable, robust, and scalable. It can flex with changing demands, it can withstand disruptions, and it can grow seamlessly. What we've created is more than just a scheduler. It's an autopoietic resource allocation system. Like a living organism, it continuously recreates and maintains itself, adapting to its environment. So this brings us to the artificial bee colony algorithm that we have already implemented in our emergent scheduling environment. So the core concept here is to conduct local auction on resource slack. In this model, we view resources as food sources, each characterized by quality value. Then we have the pods that represent, of course, our workloads, and they act as bees with specific demand vectors. Our bees or pods operate in two distinct roles. So, first, we have unemployed bees. These are constantly on the hunt for food sources, or in our case, available resources. First, the pods are considered the scout bees, which explore freely available resources in the cluster, creating so called resource agents in this pool of resources. Then we have the employed bees. These are associated with specific food sources where they are deployed. So they can change the quality of their food source if they require, for example, fewer resources than initially allocated. So thus, if another unemployed bee enters the system, it can be an onlooker bee that acquire resources from other bees based on this quality metrics. So this bio-inspired approach allows for dynamic, efficient resource allocation. It mimics the collective intelligence of bee colonies, enabling our system to adapt fast to changing demands and resource availability in the edge continuum. And this is also reflected in our simulation results, where we can improve the resource utilization and satisfaction rate by exploiting the slack resources using this bottom up approach. We compare it against a completely random algorithm and a best algorithm, but of course, most expensive in terms of computation time. What we found with the bees is a solution that shows a great utilization on improved satisfaction rate combined with a flexible local algorithm that is not computationally intense. So for further information, I'd like also here to refer the audience to our newspaper on the algorithmic part and the simulation framework we've just presented this summer at the IEEE conference on intelligent systems. And this brings me already to the end of my presentation. So thank you a lot for your attention. If you have any further questions, for sure my colleagues are going to answer them, or please write me an email if you have any more questions or any more feedback. Thanks a lot.